guys, this is our last new lesson of 2023 of the first semester. So after this, we're reviewing, testing, exam reviewing, testing. So you still have 2 or 3 sections left in Unit 2. Don't throw them away or get rid of them, okay? 2.13 on will be second semester. We'll just do those sections like by themselves and probably just have like a in-class quiz on them. And then we'll start Unit 3. Then we'll start Unit 3, which is trig in our final unit. And then after we finish that, we just review for the AP exam, okay? So other news, homework check tomorrow, and the quiz, online quiz is due Wednesday, okay? So don't forget that. Don't forget about that quiz. I'll remind you again tomorrow and Wednesday. Also, your 2.8 to 2.12 test review is ready. It's purple. It's on that little table over there. Don't go get it right now. I put it over by your phones, but I'll come around and offer it too so you don't forget if you want it early. So we'll be doing this tomorrow, about 30 minutes on Wednesday. If you're here, I'll see you guys. No, I don't see you guys on Wednesday. That's right. I don't see you guys Wednesday. So Wednesday's the fast testing. Remember, I offered you to take pictures of it if you wanted to. The schedule. So I don't see you guys on Wednesday. So you're going to have to remember, without me reminding you on Wednesday, that the quiz is due. So this is a Tuesday, Thursday review, let's call it. And then we test Friday and Monday. You'll notice when you look at it, it's only 12 multiple choice questions and 2 FRQs. So I'm going to do the test a little different this time. Instead of having a day that's test calculator and a day that's not calculator, I'm probably going to do like a day that's multiple choice and a day that's FRQ. So like one of your test days is 12 multiple choice questions. And then one of your test days is 2 FRQs. Okay? So we'll be doing some calculator swapping and stuff. We'll figure it out. Okay. So last new thing, we have 3 examples, 4 homework problems. Everything that we're doing here is review. So, except for like 2 of you missed a few days if you haven't caught up on Canvas, and you might be a little confused, so just keep that in mind. All right, so what we're doing here, basically, is it says product. It's really the power property that we're going to be using here, is taking a parent function, and they squared it, and we're going to use our power property to graph it, okay? Because if you tried to graph it with the x squared, like I couldn't really describe to you what x squared in a log is. Like if it's just x squared, I know that's a parabola. And we're restricting the domain and all that stuff. So when I see something that's not really, that I wouldn't be able to explain in transformation words, like I can't say this is left 4, up, and you'll see what I mean in a second. I know I'm going to apply a property to it. And the power property, we learned that an exponent gets written in front. So my new g of x is that. And I can explain what that means. That 2 right there is like an a value. It is telling me that my parent function will have a vertical, you can say dilation, a vertical stretch by factor of 2. That makes sense to me. So I'm just taking my parent function and I'm going to stretch it by 2. And we're going to show that on the graph by graphing both f of x, the parent function, and g of x, the transformed function. So in our calculators, go to your y equals, actually I would just clear the RAM at this point, 2nd plus 712, because a lot of people have been playing with it. And let's go ahead and start with the parent function, math alpha math 2 and x. So I'm going to give you a calculator speech right now. A lot of you watch me do it. And I'm not saying that's bad just by watching me do this, but if I asked you, like, I'm just going to use somebody as an example. Let's just use Dylan. Dylan is doing it. But Dylan, if he just sat there and watched me and I said to him, Dylan, you're not trying. How do I put this in the calculator? He would have no problem saying, math alpha math. That's how you did that, Miss Morris. That's how you put it in. That's fine, because we're doing it right now. But remember, by the time we get to the AP exam, you're going to have 5 million things to remember how to do on these calculators. The more you interact with your graphing calculator and do these problems with me, the more it becomes muscle memory. It is a thing, okay? So yes, right now while we're in the trenches doing this every day, because you hit it every day, math, alpha, math. But if you're just watching and just letting me do it and not doing it yourself, you may not be able to recall it later on. So please interact with your option calculators a lot with me. All right, so I graph it. I like to see what it looks like. And then I go to my table, and let's pick some good points. Like right away, I can see these errors starting, right? My errors are starting at 0, and that makes sense. I'm going to have a vertical asymptote right here at 0. And then let's pick some good points. We have a point at 1, 0. That also makes sense. All logs have a point at 1, 0, their parent function. And let's pick a few other nice points. 2, 1 would be a good point. 4, 2 would be a good point. Let's get one more to see it further to the right. And we have a good point at 8, 3. Okay, so now I can really see what's going on with this graph, and I can sketch the curve, arrows on the ends, not touching my asymptote, right? Okay, there's the parent function, great. Now go back and put in the g of x. So there's a 2 in front of our log. And when I graph that, okay, let's go back and talk about what this is. A vertical stretch means all of my y values are going to go up. How far? Factor of 2. Factor is multiply. So if I were writing an xy rule, which you're supposed to do in the homework, I just didn't write it here, that means all my x's stay the same, all my y's are multiplied by 2. That's what a vertical dilation does. If anything's happening up or down, it's affecting the y value. And so if you look at your table, all of your y values have been multiplied by 2. So we have a point at 1, 0 still, okay, 1, 0. And then we have another point at 2, 2. That makes sense. The 2, 1, the 1 got multiplied by 2, so it became 2. I don't even have to look at my chart. If I have a point at 4, 2, my next point would be at 4, 4. That's multiplying this y value by 2. This one would be 8, 6, because it's 8, 3. Multiply 3 by 2, we get a 6. So if we didn't have our graphing calculator to do that, we could have easily just multiplied the y values by 2. The asymptote doesn't change. The behavior of the graph doesn't change. Just the y values got stretched. It makes the graph taller, I guess you could say. Okay? So let me just label that. That guy's g of x. That guy's f of x. Last step on that problem is to describe in words what happened. So as x values increase by 1, y values, how would we say this, are a couple different things you could say here. Vertical dilation, like it said in the directions. You could say a vertical stretch by factor of 2. Okay, so that's applying the power property to a parent function. It's much easier to understand written like that than if we had kept it like that. Okay? Let's do example 7. And so this example really helps me understand, am I applying a property? Like, could I describe in words what's going on here? Yeah, this is our basic transformation stuff. We've got flips and stretches and translations, which is left or right or up and down. So if I was asked to explain this in words, I would say left 1, right? I'm going to go left 1 from there. We're going to have a vertical stretch or dilation by factor of what? What's the number? 2. What is it not? Not negative 2, right, William? It's a factor of 2. And then there's a reflection or flip. You could say either one over which axis when there's a negative in front of your a value? X-axis, right? So if you had to explain it in words, you could. So that makes me say, oh, I'm not going to rewrite my coefficient as an exponent, right? You could apply the power property there, but why would you? Okay. Could I have described this one in words? No. So it helps to use that power property the way we did it. Okay. Now we're going to find the domain. Now I showed you last week a really easy way to find the domain of logs. You just set this greater than 0. You could also say, I don't remember. I've done 5 million things in this school year, and I'm going to graph it first, then say the domain. Because a lot of times it is easier by looking at the graph. But let's just review that in case it's on your test, which I think it is. X plus 1 is greater than 0, and then you solve it. So x would be greater than negative 1. Easily, negative 1 to infinity, right? That's what it would be. But we do have to graph it, so we're going to see that anyway, so you could have gone back and done part A in a problem like this. So I'm going to just clear my RAM. It's easier than deleting both of those. And let's put this in our calculator. So it's negative 2 natural log. Notice it doesn't give you an option for a base, because natural log is always base e. And then I have x plus 1. And then I'm going to graph it. Let's see what it looks like. Okay. And then go to your table and grab some good points. You can see where our errors begin is negative 1. That's where our asymptote is. That makes sense. We just said our domain is from negative 1 to the right. So I'm going to have an asymptote that I want to respect and observe when I graph right there at negative 1. And then there's really only one good point. It's 0, 0. There's a lot of decimals here, which you can easily kind of guess where they are. But for something like this, I might just go back to the graph and kind of model that, right? Okay. So there's the graph. And now let's state some other things. So again, you could have just done part A after part B, because you can really clearly see it's from negative 1, 0, but there it is algebraically. The range of all of these logs is negative infinity to infinity, but of course you can see that on the graph. Oh, sure. Yeah. And then we have an asymptote at x equals negative 1. How do you remember if it's a vertical or, I guess you can see it's vertical. How do you remember x or y? Because that's important. Remember vax hay. So it's a vertical, so it's vax. Okay, so keep those little tricks in your mind. There's an x, there's one intercept, that's at 0, 0. It's the only place it touches an axis. Now, function behavior and concavity, there's a lot. That's like a very big umbrella, vague thing. When we're talking about logs, it would probably want you to talk, well, it says concavity, like what is decreasing and increasing like we did last week. There's no mins or maxes. That would be function behavior. Is it continuous? Is there any hole? Are there any holes? Things like that, okay? But for these, we usually talk about concavity, which, what would you guys say that one is? It's up. So let's use that to state what the rate of change is doing. The rate of change, is it going to be increasing or decreasing on concave up? Increase. Up is increase. But is the function increasing or decreasing? That's really visual. What's happening as we go left to right? Are we going up or down? Down. So that's decreasing. So I keep pointing these out because those right there, we talked about this last week, but real quick, rate of change and function behavior, increasing and decreasing, same words, different concepts, okay? And that was something from Unit 1 a lot of us got confused on. So that's why I like that it's coming back, because we're going to have to remember all this for the exam. Last thing, I am going to be, in the past tests that we've had so far this year, I have not been really strict about if your limit behavior notation, your limit notation was properly written. From now on, it's going to be something I look at on your FRQ. So let's practice this in our homework, so it's second nature. So limit, and then name your graph correctly. Go back and see, what is this function called? His name is f of x. Don't call him g of x, that's rude. The limit is f of x, the limit of f of x as x approaches something equals something. I'm just setting it up right now. And I write the same thing 2 times because there's 2 ends to our graphs. There's a left and a right, so we always have 2 of the same exact things. and then we fill it in. Okay, so let's do left-handed first, left-sided. As x approaches, goes to the left. So as x goes towards negative infinity, is there anything blocking it from going all the way to negative infinity? The answer is yes. This asymptote affects our end behavior. It's blocking us. So we're approaching -1 from the right. And what are the y values doing? They're going up. So what goes here is, where's x traveling towards? Where's y traveling towards? Okay. As we go to the right, so as x approaches infinity, there's nothing blocking it. It gets to happily go to the right forever. So the x values are going to the right. What are the y values doing? They're going down, right? Y values are slowly going down towards negative infinity. I think you guys are getting really good at end behavior stuff. I think you're starting to really click with you. One more to do, and this one's really important because there's a question like this on your test. And remember I told you when the x is written like that, it's a little bit tricky. Here it is again. Okay, it is on your test. I mean, not this exact question, but this concept. Okay, so am I going to use any properties for this one? Am I going to rewrite this one a different way? I am. I don't know what 3 minus x squared means in a log. That's not something I know how to say in words. I can apply my property, my power property here, and make it 2 natural log of 3 minus x. And when I do that, I could easily describe all of the transformations. If it asked me for that, I would have to do that. This question is not asking me to do that, but the one on the test is. So let me finish the problem, what it's asking for here, and then I'll do a quick, how would you say the words for this one, okay? So domain, again, I'm in log, the chapter about logs, so I easily remember that I set that greater than 0, but again, you could do part B first and see it. But let's practice doing this. So I would subtract 3, right? I'm going to go this way. I would subtract 3, so I would have negative x is greater than negative 3. But don't forget, when you divide by a negative number, you have to flip your inequality symbol. Okay? So negative 1 divided here, negative 1 divided here gave me a positive x and a positive 3, but I remembered to flip my inequality symbol. So my domain, sorry, let me squeeze it right here, would be from negative infinity to 3. All the numbers less than 3. That's going to the left. And we always do interval notation, least to greatest. Okay? Now let's graph it. Yay, we get to go to our calculator. So clear out that last one I did. 2 natural log 3 minus x. Let's see what it looks like. Okay, it makes sense. Look at our domain. It's from negative infinity to 3. We are going to have an asymptote there. So let's go to the graphing calculators table, and I see a good point at 2, 0. And then I see at 3 where the error starts. And as I scroll through, I see lots of decimals. I can do a nice, easy sketch by looking at that picture. Okay. There's the graph. The range of all these, whether you look at the picture or you just remember, negative infinity to infinity. Ooh. We have a vertical asymptote at x equals 3. We have 2 intercepts. 2. We have an x-intercept, pay attention here, x-intercept at 2, 0, and a y-intercept at a decimal. Okay? So we could go to our table and find when x is 0, y is this decimal answer. So technically that is the answer, but that's a rounded number. Okay? This is an infinite, this number goes on forever. It's the word. Can't think of it. Irrational. Thank you. Who said that? Good job. Irrational. So here's a better way to write it. Remember I told you would see this on the test. Anytime you have a point on the y-axis, x is 0. You can very easily put a 0 right there. Okay? Let me just write it real quick. You don't have to show this work. I'm just going to make sure you guys understand. If I put a 0 there, what do I get? That. 3 minus 0 is 3. That answer right there is the same exact answer. If you put it in your calculator, it would go 2.1. That number would be that number. Okay? This is called an exact answer. It's kind of like when we did quadratic formula, you would get like the square root of 17, which is irrational. Put it in your calculator. So you say, oh, I'm just going to leave it as the square root of 17. It's exact. We're not rounding it. Okay? So you'll see that. Function behavior. Okay, this one's a skip through these. Concave down. Okay? Concave down, which means my rate of change is decreasing, d, but the function is also decreasing in this case, right? Going down. Limits. Limit of what's your name? Your name is g of x. You guys are making it easy for my decisions for seating chart next semester. I am changing seats. Okay, so we write the same thing twice. What's happening to the left? X is traveling towards negative infinity with nothing to stop it, right? It's going to the left. There's nothing there that's stopping it. He can go as long as he wants towards negative infinity, and our y values aren't blocked by anything. They're going up forever, right? This is different, though. Anybody want to try it? What are we approaching as we go to the right? What are we approaching? 3. But what else do I have to write? From the left. If someone was just reading that, they wouldn't know that you can't have points over here. This is saying we're approaching 3 from the left. There's no points over there. But there's nothing limiting our y values. They're going down forever. Okay? Now, real quick, this right here, if I had to put in words, and that's what the test question is, okay? It's not doing all this, and it's a non-graphing calculator question. So if I said, describe all the transformations, I think we all know the 2. It's a stretch by a factor of 2, so I'm not going to write that. But the 3 minus x, look. This is on the test, and it can be tricky. Remember, you want to rewrite it with the x going first. Okay, so the x is negative, 3 is positive. And then remember, I factor out the negative to make the x positive. When you take a negative away from these two, it changes their sign. It's like the reverse of the distributive property, right? This is negative x. Negative times x is negative x. That's a positive 3. Negative times negative is positive. When you see it written like this, you can easily say this is a flip over y-axis, because it's still in there with the x. Remember, a negative in there, that's a flip over the y-axis, which looks like what happened. And then look at that minus 3. That would be right 3. And we did. We moved right 3. All of our points are going to the right 3. The parent function point would have been right here. And then move them all 3. Okay? So remember, this way, know how to do this right there. And you'll see it on the test, but I think the review question isn't that tight. That's why I'm pointing it out. So if that's something you need help with, start, whatever, remind yourself in those 2 review days that you're going to need me to help you with it. I will happily do it. Okay. Any questions before I give you the homework? Okay. All right. It's B22, 1, 2, 5, 6. So these 4 problems, please write it down so I can start putting the key up. Remember, if I went too fast over anything, you need help with the calculator, ask me. Do not just copy the homework. Use it as a guide. Try to do it, and then check. Okay. You should all have it written down by now. Yeah, let me just stop the recording.